Welcome to Dr. Nakamura's lecture series on structural dynamics, number C-5. Chapter 7, Seismic Design of Bridges. As an application of structural dynamics, I introduce how to design bridges against earthquakes. 7.1 Introduction. Seismic means earthquakes, which is the ground motions in three directions: longitudinal, transverse, and vertical. For the seismic analysis and design, we use the unit acceleration meter per square second, velocity meter per second, displacement meter. A very strong earthquake attacked Kobe in 1995. It was magnitude 7.3. Lots of buildings and bridges collapsed. I lived in Kobe at that time, experienced and witnessed this disaster. This is one of the worst incidents. The RC piers collapsed over several hundred meters. Hundreds of houses collapsed like this. This was a two-story house. The earthquake occurred early in the morning. You can imagine what happened to the people who slept on the first floor. More than 6,000 people died. Fire occurred after the earthquake. I took this photo 4 days after the earthquake. Smoke still came out. Lots of RC piers damaged at the top or bottom parts. This pier nearly collapsed. This continuous plate girder bridge collapsed when the RC pier crashed at the intermediate supports. This is a railway bridge. RC pier broke, which collapsed the girder. Adjacent girders are connected by the seismic stoppers to prevent the girder falling down. However, the seismic stopper did not work on many bridges. You can see bearings were collapsed and the seismic stopper was broken. The girder had fallen off from the abutment. To prevent this, the stopper is essential. This is a simply supported railway bridge. The girder fell down from the abutment. Only the rails survived. We learned a lot from this tragedy to design a safe bridge against such a big earthquake. I was engaged in construction of the Akashi Kaikyo Bridge in Kobe. When the earthquake occurred, the main cables were just finished connecting the towers and anchorages as shown in this photo. The active fault lies between the two towers. This active fault triggered this earthquake. This shows the active fault near the Akashi Bridge. You can see the ground moved vertically and horizontally. This person was my colleague, about 160 centimeters tall, demonstrating the scale of the ground slide. This road was almost straight, which was separated by the active fault. The ground moved 3 meters horizontally, 1 meter vertically. The earthquake affected the Akashi Bridge. This shows the dimension of the bridge layout before and after the earthquake. The main span expanded 0.8 meters. The cable went up 0.13 meters. This geometry change affects the structural members. The cable stress increased by 0.6%, the tower stress by 18 megapascal. Fortunately, the bridge was under construction and we could adjust these changes caused by the earthquake. 7.2 Basic equation for seismic analysis. 7.2.1 Single degree of freedom structure. Seismic means earthquakes, which is the ground motions in the three directions: longitudinal, transverse, and vertical. Suppose a single degree of freedom model is subjected to the seismic motion. The ground moves and displaces UG. The mass M vibrates and displaces U in the local system. And the total displacement from the original position is U0. The dynamic equation of this system is expressed by equation 1. As shown in the figure, U0 equals UG plus U, which is put into equation 1. Then we get equation 3. The right side of this dynamic equation is the external force. Therefore, for the seismic analysis, minus MUG2' works as the seismic force. 7.2.2 Dynamic equation for seismic analysis of MDOF structures. For seismic analysis of MDOF structures shown in this figure, dynamic equation of matrix form can be expressed by equation 4. The right side of this equation is the seismic forces which work at each node with mzg2', where zg2' is the ground acceleration and E is the unit vector. 7.3 Basic principle of seismic design. Japan is in the seismic zone and suffers severe earthquakes. I explained the seismic design specification for road bridges in Japan. You can learn how we tackle these dynamic problems caused by earthquakes. 1. Types of earthquakes. We classify the design earthquakes into two categories: Level 1 L1 earthquake and Level 2 L2 earthquakes. L1 earthquake is the design level earthquake which is likely to occur during the design life. L2 earthquake is the ultra-strong earthquake which is less likely to occur but very strong. L2 has two types: Type 1 plate tectonics type and Type 2 active fault type. Type 1 is caused by the sudden slide of the plates surrounding Japan, and the dominant period and the duration are long. Type 2 is caused by the sudden slide of the local active fault, and the dominant period and the duration are short. 2. Important grade of bridges. Bridges are classified into two groups due to its social and economic importance. Class B is highly important bridges on such as highways and national roads. Class A is the standard bridges on such as local and rural roads. 3. Target or required performance. It depends on earthquake levels and importance of bridges. For L1 earthquake, no damage is allowed for all the bridges. For Level 2 earthquake, minor damage is allowed but no collapse for Class A bridges, whereas not major damage and easily repaired for Class B bridges. 4. Design method, which is different for earthquake levels. For L1 earthquake, seismic coefficient method is most commonly used. For L2 earthquake, ductility or capacity design method is used considering energy absorption property of a bridge. These design methods will be explained in detail later. 5. If bridges have a complex structural form with MDOF, such as arch bridges and cable-stayed bridges, more sophisticated design methods are applied, such as spectral response method with modal analysis and time history analysis. 6. Total anti-seismic system. We have to prevent the bridge girders falling off from piers and abutments. Therefore, the girders are jointed to piers and abutments. Also, the girders are connected to each other with the seismic link. 7.4. Seismic coefficient method. This is the most common design method for the SDOF structures subjected to L1 earthquake. Suppose there is a continuous girder bridge as shown here. Then pick up this unit consisting of the pier and the girder. It can be modeled as a SDOF model. The seismic force is assumed to act on the node as the design lateral force H. H equal KHMG equation 5, where KH is the design seismic coefficient, mg is the self-weight of the girder. KH equal CZ KHC0 equation 6. CZ is the area factor which depends on the seismic intensity in the area. KHC0 is the standard seismic coefficient which depends on the natural period of the structure and the ground condition. This graph shows KHC0, the standard seismic coefficient for L1 earthquake. The x-axis is the natural period of a structure and the y-axis is KHC0. There are 3 lines which are used for 3 ground classes. Ground class 1 is a solid and hard ground. Class 3 is a very soft ground and class 2 is in between. KHC0 is highest for class 3, followed by class 2, and class 1 is the lowest. It decreases with the longer natural period of a structure. When a SDOF model is subjected to a lateral force H, it displaces with delta. In general, delta increases proportionally with H in the initial stage, but it increases exponentially after H reaches the yield point. A structure is verified its safety by equation 7. The seismic lateral force H should be less than the yield force over the safety factor. Exercise 7.1. Suppose a bridge superstructure with a total weight of 2W is supported by the piers, as shown below. Find the horizontal seismic coefficient, the horizontal seismic force, and the bending moment at the bottom of each pier under the following cases. 1. L1 earthquake. ground class 1, natural period 0.7 seconds, CZ equal 1.0. 2. L1 earthquake, ground class 2, natural period 2.0 second, CZ equal 1.0. 1. L1 earthquake, ground class 1, natural period 0.7 second, CZ equal 1.0. KHC0 is found 0.2 from the figure and equation. So H becomes 0.2 W and M is 0.2 WH. 2. L1 earthquake, ground class 2, natural period 2.0 second, CZ equal 1.0. KHC0 is found 0.188 from this equation, and H becomes 0.188 W and M equal 0.188 WH. 7.5. Ductility or capacity design method for L2 earthquake, SDOF. If the seismic coefficient method for L1 earthquake is applied to L2 earthquake, a bridge may have an unrealistic and uneconomical structural form. We need more rational design method for the ultra-strong earthquake. The seismic force H is H equal KHmg, same as the seismic coefficient method. KH is the design seismic coefficient and KH equals CZ CS KHC0 equation 8. CZ is the area factor and KHC0 is the standard seismic coefficient. CS is the structural coefficient defined by equation 9. Mu is the ductility factor. CS considers the ductility of a structure. When a structure has a good ductile property, CS and eventually KH can be small, whereas when a structure has a poor ductility property, CS and eventually KH can be large. These graphs shows KHC0, the standard seismic coefficient for L2 earthquake, type 1 and type 2. There are 3 lines which are used for 3 ground classes. KHC0 for L2 earthquake is much larger than that for L1 earthquake. For ground class 1, the maximum value of KHC0 for L1 earthquake is 0.2. That for L2 earthquake type 1 is 1.4. That for L2 earthquake type 2 is 2.0. Let me explain the structural coefficient CS and ductility factor mu. Suppose the SDOF model is subjected to the lateral force P, it displaces delta. Compare these two relations of P and delta. Both curves are linear until delta y, the yield displacement. The structure with the green curve sharply decreases after the peak with the ultimate displacement delta U. The structure with the blue curve continues to increase until the peak with the ultimate displacement delta U. The ductility factor is defined by delta U over delta Y. The structure with the blue curve has high ductility and is ductile. The structure with the green curve has low ductility and is brittle. Obviously, ductile structures are favored. The equation of Cs is derived by the constant energy law, which means that the area of OEF is the same as the area of OYUV in the figures of P delta curves shown here. The relation of OYE is for the elastic structure, and that of OYU is for the elastic plastic structure. The ductile structure can be treated by the elastic plastic structure. This constant energy law of equation 10 leads to these calculations. Please follow them by yourself and finally get equation 11. Exercise 7.2. Suppose a bridge superstructure with a total weight of 2W is supported by the piers as shown below. Find the horizontal seismic coefficient, the horizontal seismic force, and the bending moment at the bottom of each pier under the following cases. 1. L2 earthquake type 1, ground class 3, natural period 0.5 second, mu equal 2.0, Cz equal 1. 2. L2 earthquake type 2, ground class 1, natural period 0.7 second, mu equal 5.0, Cz equal 1.0. For case 1, Cs is calculated by this equation with mu of 2.0. KHC0 is 1.2, then KH becomes 0.693. Then H is 0.693 W, M is 0.693 WH. For case 2, Cs is calculated by this equation with mu of 5.0 and KHC0 is 2.0, then KH becomes 0.667. Then H is 0.667 W and M is 0.667 WH. 7.6 Dynamic analysis for MDOF structures. Usually, complex structures are the MDOF system and needs advanced methods to analyze their seismic behaviors. In this lecture, time history analysis and response spectral method are explained. 7.6.1 Design seismic waves. We use the seismic waves for these analyses. This is the design seismic wave for L1 earthquake, which is obtained by many actual earthquake data. The maximum acceleration is about 100 cm per square second. These are the design seismic waves for L2 earthquake type 1 and type 2. Please note, in type 1, the duration time is long and the dominant frequency is relatively long. In type 2, the duration time is short and the dominant frequency is relatively short. 7.6.2 Time history analysis. Suppose this 3 degree of freedom structure is subjected to the seismic waves ZG2' at the base. Seismic forces MZG2' work at each node in the opposite direction. The dynamic equation is expressed by the differential equation 12, which can be numerically solved. One of the common methods is linear acceleration method, where u2' at t is used to calculate u2' at t plus delta t the next step. I show you an example of time history analysis. We studied seismic behaviors of this multi-span cable-stayed bridge with 3 different connection methods between the girder and the tower. The girder moves free MOV, connected with the linear spring LS and connected with the bilinear spring BLS. When this bridge is subjected to the design seismic wave of L1, the displacements at the top of the tower P4 were calculated as this graph. You understand the MOV gives the largest response, followed by LS. BLS is the lowest and effective to reduce the response. 7.6.3 Response spectrum method with modal analysis. In this method, you have to understand 2 concepts, modal analysis and response spectrum. A. Modal analysis. Look at this 3 degrees of freedom structure. You already learned its dynamic equation consisting of mass matrix, displacement vector, and stiffness matrix. Let us calculate with these specific values. M1 is 750 kg, M2 1500, M3 1500, and K1, K2, K3 are 100,000 Newton per meter. Mass matrix, stiffness matrix are obtained like this. Then we can calculate natural circular frequency by this determinant equation. 3 natural periods are obtained like this. Next, we can get mode shapes by equation 14. As you understand, there are 3 modes and the 3 shapes are obtained like this. This shows the concept of modal analysis, where this 3DOF model is subjected to seismic ground acceleration. It vibrates like this. This response is assumed to be superposed of 3 basic modes. Q1, Q2, Q3 are contribution factor of each mode. Therefore, the displacement at node I, Ui, is expressed by equation 15. There is an important property about the mass and stiffness matrix. Response Ui can be calculated by equation 15. Equation 16 is a basic mode equation. To study the relation of each mode, multiply phi j to equation 16 from left and phi I from right. It is found that only when I equals j it has a value. It is 0 when I is not j. The value Mn is called generalized mass of the nth mode, and Kn is called generalized stiffness. This property is called orthogonality of modes. Equation 17 is a dynamic equation with the seismic forces. Using the modal analysis of equation 18, putting it to equation 17 and multiply phi from left, we get equation 19. Dividing it by Mn, equation 20 is the basic dynamic equation for the seismic analysis. Beta n shows how much each mode affects the response of the structure, which is called the contribution rate of the nth mode. B. Response spectrum, which is another concept used for this method. Suppose a 3DOF model is subjected to an earthquake wave. There are 3 independent modes. The response of each mode is calculated by time history analysis. These are the acceleration response of the 3 modes. Find the maximum acceleration of 3 modes, SCA1, SCA2, and SCA3. This graph shows the maximum acceleration versus the natural period, which is obtained by time history analysis. SCA1, SCA2, SCA3 correspond to these points. There are 3 response spectrums: SCA, acceleration spectrum, SV, velocity spectrum, and SD, displacement spectrum. They show different curves. SD increases with the natural period, SCA decreases, and SV is flat. SD, SV, and SCA have these relations. Exercise 7.3. Suppose the 3 degrees of freedom model, figure 1, is subjected to the earthquake. Find the maximum displacement at the nose, the base shear, and the bending moment at the base. Note that M1 equals 750 kg, M2 1500, M3 1500, and K1, K2, K3 are 100,000 Newton per meter. The acceleration response spectrum is shown in figure 2. The natural periods and mode shapes of the given model are already obtained in the previous example. The generalized mass M1, M2, M3 are obtained by these equations. The contribution rate beta 1, 2, 3 are obtained by these equations. The acceleration response of 3 modes SA1, 2, 3 are found from figure 2. The displacement maximum response is found by this equation. The maximum displacement at each node, U1 max, U2 max, U3 max, can be found by summing up the response of 3 modes. But it is known that the root mean square is appropriate instead of the simple summation. The maximum shear force Q max can be found at the root mean square of 3 modes. Also, the bending moment at the base is found as the root mean square of 3 modes. This is the end of the lecture series on structural dynamics. There are other my lecture series. So, see you next lecture series.